All right, so let's take a look at a titration where instead of adding a strong to a strong, we are going to take and add a strong. So the strong will be in our burette, it will be the titrant, and the stuff that we'll be analyzing is something that is weak. And so in this case, what we're going to do is we're going to add sodium hydroxide into a solution of acetic acid. We're going to have a completely different titration curve or different plot. And what's going to happen is we're going to start out with a weak acid. And as we add our strong base, we're going to realize that we are going to create a buffer. We're going to discover that as we do this, halfway to the equivalence point, pH is going to equal pKa. As we go up to the equivalence point, we're not going to have a pH of 7. It's in fact going to be basic. And after a pH of 7, we're going to have strong base in excess. And again, the only way to do this is just to do the math. So let's do it. So we're going to titrate 40 mils of 0.2 molar acetic acid with 0.2 molar sodium hydroxide. First of all, at the equivalence point, when we're 1 to 1, we'll have added 40 mils of the base. Halfway to the equivalence point, we will have added 20 mils of the base. Initially, none, and we're going to do 1 mil past. So let's start out with the initial question. If we want to know the pH initially of acetic acid, we're going to realize that we have 0.2 molar acetic acid. We don't need the volume because it's going to be irrelevant. All we're going to do is need the molarity. We know this is a weak acid, which means we need a Ka, we need an ice, we're going to do an X, so we can look this up. If we look this up, we're going to find that Ka is 1.8 times 10 to the minus 5, and we know how to do an ice chart on this one. So acetic acid is going to react with water. We're going to make the acetate plus some hydronium. If we do our ice chart, we're going to have 0.2. We're going to ignore the water because it's a liquid. I have 0 of these to begin with. Minus x, so 0.2 minus x plus x, x. And if we keep going on this, we can plug it into the equation and we can solve for our pH. So plugging this into our equilibrium expression, we're going to get 1.8 times 10 to the minus 5 equal to x squared over 0.2 minus x. We're still going to set that bottom x equal to 0. And when we solve for this, we're going to get x is equal to the concentration of the hydronium. And when we get the x is the concentration of hydronium, that value is 0.0019 molar. pH is a minus base 10 log of that, and pH is 2.72. So it's a weak base, and instead of being a pH of down 1-ish, which it would be with a strong, it's going to be a pH of about 2.72. All right, next one. Halfway to the equivalence point, we're going to start with the takeaway. Halfway to the equivalence point, pH equals pKa. For any weak titration, this is going to be our equation halfway to the equivalence point. But let's make sure we can do it first. So what are we doing? We are taking and we are adding sodium hydroxide to a weak base. Well, we know how to do this. We know that we're going to take OH minus, and we're going to add it to our acetic acid, CH3COOH. Because this is strong, it's going to be one arrow. It's going to make acetate and water. Now we're going to ignore the water because it's a pure liquid. Again, because this is strong, we are going to need an ICF. Okay, this is not the ice chart anymore. We're adding something strong. We're going to have to do our moles. So the concentration of sodium hydroxide is 0.2 molar. So we're going to have 0.020 liters multiplied by 0.2. And that's going to give us 0.004. Our acetic acid is 0.040 liters multiplied by 0.2, and that's going to give 0.008. This is 0, and this is going to be ignored. This is going to go down by the smaller of the two values because it's a limiting reagent. Minus 0.004 minus 0.004, and don't forget, add the 0.004 over here. We're going to make some acetate. So that at the end, I have no sodium hydroxide. I have 0.004 moles of the acetic acid, and I have 0.004 moles of the acetate. Now, we're going to reevaluate at this point every time. And when we do this, we're going to realize that we have buffer. We have a weak acid, and its conjugate base. You know when we have a buffer that pH is equal to pKa plus the log of the base over the acid, which is equal to the minus base 10 log of 1.8 times 10 to the 5 plus the log of the base over the acid. Now remember, we do not have to actually do molarities here. We could do moles. Why? Because the volumes are constant and they will divide out. And we're going to have 0.004 over 0.004. So what is the point here? Halfway. Well, halfway, this is going to be equimolar. Our concentration of our base will equal the concentration of the acid. If that is the case, this term is 0, and our pH is going to equal pKa. And so our pH of the solution is 4.74. This is going to work for any time we are adding a strong to a weak. At the halfway point, pH is equal to pKa. All right, now this was the fun point in the last question, but here this one isn't any fun whatsoever because we're going to have to do a bunch of math on this one. We're at the equivalence point. The equivalence point is going to tell us that the moles of sodium hydroxide added will equal the moles of the acetic acid in the solution. What does this mean? Well, this means that we're going to take OH minus, we're going to react it with acetic acid, we're going to make the acetate and some water. So, because we're adding something strong, we need a mole chart, so we need ICF. This is going to be 0.040 liters multiplied by 0.2 molar, 0.040 liters multiplied by 0.2. We're going to assume that one is 0, and we're going to realize that these values are the same, that we have the same amount of hydroxide as we have acid. Well, that is the definition of the equivalence point. So all of both the hydroxide as well as both of the acetic acid are going to react. Don't forget that what that means is we're going to create the equivalent amount of the acetate, leaving us 0 moles of hydroxide, 0 moles of acetic acid, and 0.008 moles of the acetate. Go. Okay, well, so what? Well, this is the conjugate base of a weak acid, which means this solution is going to be basic. And because this is the conjugate base, immediately this tells us that this is like a salt question, which means we're going to have to calculate our K, in this case a KB, and we're going to have to do an ice chart and do the rest of that mess. So with that in mind, we have 0.008 moles of the acetate. It is in a total volume of 80 milliliters. Remember, we had 40 plus 40, 40 mils of the acid originally, plus 40 mils of the sodium hydroxide added, for a total of 80 mils. So we're going to divide this by 0.080 liters, and we're going to get a concentration of the acetate of 0.1 molar. And we know that Ka for the acid multiplied by Kb for the conjugate base is equal to Kw. So Kb for this base is going to equal 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. That's going to give us 5.6 times 10 to the minus 10. So now what do we have? Well, we have a concentration, we have a K, we know this is weak, so we need an ice chart. So CH3COO minus, going to react with water. All of the strong is gone. We're back to our double arrows in our hydrolysis. And we're going to need ICE. Again, ICE again because it's weak. 0.1, 0, and 0 minus X, 0.1 minus X. It's going to start looking familiar. And we're going to get 5.6 times 10 to the minus 10 is equal to x squared over 0.1 minus x. Now notice we're going to set that small x equal to 0. And when we solve for it in the numerator, we're going to get x, which is the concentration of hydroxide, is equal to 7.5 times 10 to the minus 6 molar. POH, because this is hydroxide, we got to do that step first, is 5.13, and pH is equal to 8.87. All right, so if we graph this, we're going to start out with a weak acid. As we do this, we're adding strong base. And as we start adding strong base, we are going to take our weak acid and convert it into its conjugate base. Because if we add hydroxide to some HA, we are going to make A minus and some water. So when we start, we have all HA at the very, very beginning, all weak acid. At the equivalence point, I should change colors here. At the equivalence point, we're going to have all A minus. So all HA here and all A minus there. In the middle, we're going to have a buffer because we're going to have both HA and A minus, which gives us a completely set of different problems. After we go past the equivalence point, we're going to have strong base in excess, and we're going to have excess OH minus. The only way to do these is just to walk yourself through them very slowly and carefully, realizing that our magic point on this curve is halfway, and halfway pH is equal to pKa, and you don't have to do the math. So how might we monitor this? Well, we would actually take our pH meter and take the pH. We would add the sodium hydroxide carefully while monitoring the pH, and then we'd get our graph. Endpoint is usually measured with an indicator rather than the pH. Endpoint is frequently a visual endpoint. That's when like the color changes. Here, we can use an indicator as a function of what the pH is going to be at the endpoint. And that, if we had a titration curve, so if we start out with weak, goes up into a buffer, and then it goes up very, very strongly, and then levels off. Halfway right up that curve right there is the equivalence point. That is where the moles of the acid are equal to the moles of the base. On this graph, halfway to that point would be pH equals pKa. In the middle here is a buffer, and if we're lucky and our indicator changes color right there, our endpoint would equal our equivalence point. Frequently, it's a little high or low, but nonetheless, we use a visual indicator, just put a solution in that changes color with pH to figure out what our end of this reaction is going to be, what our endpoint is.